Dear faculty members, dear students, dear guests, I would like to introduce the lecture of Professor John Manning, who is with us at the invitation of the Department of Anthropology. Today's lecture is the second of the 3 lectures Professor is going to deliver in Łódź, and it refers to the digit ratio as the marker of various physiological and developmental events. Today, Professor Manning is going to tell us about the relationship between the sex ratio, between the digit ratio, sex and ethnic, and also national differences. As I said, this is the second lecture, and for those of us who did not attend yesterday, I would just say that the research of Professor Manning is focused on the indicator traits associated with prenatal and adult sex steroids and developmental instability, so fluctuating symmetry. This includes a focus on developmental disorders, autism, Asperger's hyperactivity, ADHD. Professor Manning is an author of numerous books and a large number of research papers. For those of you who didn't look at the CV, please do that at our website. It's really impressive. So I won't be talking about numbers, but it's really impressive. Professor Manning is also a member of various interdisciplinary research groups encompassing such people as physicians, psychologists, sociologists, biologists, geneticists, and also anthropologists. In our faculty, in our university, a similar research is being done by the Department of Anthropology, and the professor is collaborating with the department. Professor Manning, the lectern is yours. You're welcome.
Thank you very much. Thank you. Can you hear me? Yes. Okay. Yes, this is the second of my talks. There's another one tomorrow, and I'm really enjoying myself at the university, and it's an honour to be in the Department of Anthropology today. What I want to do is, because I'm in anthropology, I want to focus on 3 things in terms of digit ratio. One is its sex difference, another is its ethnic difference, and the third is its national difference. And I want to look at some of the implications of these 3 things, and try to take you through some of the theoretical aspects of this and the importance of this. This trait's a very tiny trait in the fingers, a tiny sex difference. It's not the kind of sex difference that one sees in terms of height, for example, in humans. It's a very small sex difference. But the interesting thing about it is, the thing that interested me initially, is that it's there at birth, and it remains throughout development. It doesn't change at puberty. So you're kind of stuck with it. It's fixed in your fingers like a living fossil. And it tells us something about, I think, the amount of testosterone, the amount of estrogen you've been exposed to towards the end of the first trimester of pregnancy. So that is the substance of the trait. But it's a trait that most people are not aware of, unless you read some of the literature. Okay, so what actually is the trait? Well, it's the relationship between the length of the index finger and the length of the ring finger. And the length of the ring finger is our indicator of prenatal testosterone. And so that the longer the ring finger, the more prenatal testosterone you have. But you have to adjust this for body size, obviously. So one way of adjusting it is to divide it into the length of the index finger. So it's 2D, the second digit, divided by 4D, the 4th digit, and that gives you the ratio between these 2 fingers. Okay? In this case, it's 0.95. So the ring finger is slightly longer than the index finger. This hand is the hand, happens to be the hand of a male, and it's that small difference indicated by the ratio which this individual is stuck with for the rest of his life. He was born with it, and he'll die with it. And it is an indication, we think, of the amount of testosterone relative to the amount of estrogen he's experienced. And there is a sex difference in this ratio on average, but there is a very substantial overlap. So here are a couple of hands. This is the hand of this male with a ratio of 0.95, and here we have a female where there is a difference between the male and the female, where the ring finger is not quite as long relative to the index finger. And that's the kind of average difference. If one looks at 1,000 males and 1,000 females, the difference in the ratio is quite small. But nevertheless, if you measure it accurately, it has some significance. How do you measure it? Well, the best way is from X-rays. So you take this point here, which is the proximal point of the proximal phalanx, and to the tip. Okay, that's the fourth digit, made up of 3 phalanges, and there's the second digit. All right. Now, I'd love to do every study I do, every study that everybody does on digit ratio. I'd love it to be the case that we measure the actual bones, the phalanges, but in fact, what we often do is to measure the palm of the hand and use soft tissue measurement. We were dependent on terrestrial life in terms of our limbs, our pentadactyl limbs, but we were also dependent in terms of terrestrial life on our reproductive system. We had to rejig the reproductive system, so to speak. So internal fertilization, the evolution of the penis, and the whole range of terrestrial reproduction, including the cleidoic egg and the subsequent evolution of the placenta, is really got started with this transition to terrestrial life. And with this transition, we got the evolution of the pentadactyl limb, our 5-fingered limb. So fingers and penises and internal fertilization and the cleidoic egg and the placenta are all stuck together in a whole bundle of developmental genes. So what's the secret of getting into this bundle? Well, maybe the secret is looking at the relative lengths of the second and fourth digit, or the index and ring finger, in other words 2D, 4D. So the idea is, if you measure that, what you've got is a measure of prenatal testosterone, okay, in the length of 4D, and prenatal estrogen in the length of 2D. So we've got the ratio between these two variables. Now, if you want to actually prove that, you've got to get into the fetus at the end of the first trimester of pregnancy. You can't do that in human fetuses. It's a very dangerous thing to do. But people have been looking at this in an experimental way in mice and in rats and in some primates. And in other vertebrates. I've just looked at a paper where they've looked at 2D, 4D in cows. If you know anything about the legs of cows, you'll see how quite difficult that is, but they did it. So it's so interesting that this kind of stuff is going on not only in humans, not only in primates, not only in rodents, but in artiodactyls and in reptiles and amphibia and in birds as well. So that might not enthuse you, but it enthuses me. Okay. So Zheng and Cohen published a paper on mice. That's let me just show you some of. Oh, there's that. Let me just go on Zheng and Cohen's stuff, and now I'll go back to those two slides. So the idea is, if you look at a fetus, the fingers are packed, sitting on the phalanges, are these receptors, these androgen receptors and estrogen receptors. So they're receptors to the hormones testosterone and estrogen. And if you look at these two digits, there are more of these receptors on the ring finger than there are on the index finger. The ring finger is packed with both androgen receptors and testosterone receptors. If you take the in utero environment of a male who is producing testosterone from his testes round about the end of the first trimester, he has got a lot of testosterone and very little estrogen. Testosterone accelerates the growth of the fourth digit. Estrogen reduces the growth of the fourth digit. So this individual ends up with a fourth digit that looks like that, and a second digit that looks like that. And if you look at this chap's fingers, you can see the disparity between those two fingers. The difference there is about 1 centimeter in length. Okay? Now that's a rather extreme ratio. It's not the kind of ratio you see very often, but if you're looking at very, very good sports people, you in fact quite often see a ratio like that. On the other hand, if you look at female fetuses, then they are producing some testosterone, for example from the adrenal glands, but not very much. So the ratio between their testosterone and estrogen is different. Okay? And the effect on the fourth digit is more or less the same as the effect on the second digit. So we end up with fourth and second more or less the same length. So if you think about male 2D, 4D, then you may be talking about on average a ratio of about 0.98, 0.97. If you're thinking about a female ratio, you're thinking about a ratio of about 1 in Caucasians. But of course there is a very strong overlap between the sexes. Okay? The difference is not very substantial. Now, it's okay to make to suggest these kind of models and suggest these kind of ideas, but then people want to know whether it's correct or not. Okay, and as I said, it's very difficult to actually directly look at these ideas. So there is a tendency, because you can't get into a human fetus at the end of the first trimester, you can't draw off samples of blood from a human fetus or amniotic fluid round about that time. It's very, very dangerous to do so. So one can look at direct studies of fetuses, but in mice and rats and maybe some primates. Or you can look at indirect studies in humans. And for example, indirect studies would include looking at traits, and this is an important thing, an important aspect of this. You look at traits that show a sex difference. Okay? Diseases like autism, prostate cancer, frequency of heart attacks, sports performance, hyperactivity, and so on. Things which show marked differences between males and females. That would be a kind of indication, a flag, that maybe digit ratio has got something to tell us about these traits. And certainly with sports performance, running speed and so on, there's a reliable sex difference there of about 10%, certainly with middle distance and long distance running. And if you look at digit ratio in relationship with traits like that, particularly sporting performance, you will see that it reliably predicts the outcome. It reliably predicts running speed in a 10,000 meter race, for example. You can look also at things like timing of pregnancy across the year and see that light levels, depending on light levels at the end of the first trimester of pregnancy, have an effect on digit ratio. And that was shown in 2017 by Anita Zved and her group. You can also indirectly look at clinical studies, congenital adrenal hyperplasia. Okay, that's a trait where there is excess androgen, high levels of androgen at the time of the end of the first trimester, and individuals with congenital adrenal hyperplasia tend to have masculinized digit ratios. There are also individuals who have who are not sensitive to androgen. They have androgen insensitivity, AIS, and even if they're male and they have this condition, they have female digit ratios. There's been 2 studies on that. They're not very common, these individuals, so it's difficult to work on. And you can also look at males who've got an extra X chromosome, or maybe 2 extra X chromosomes, or 3 or 4. And these males have what is known as Klinefelter syndrome. Okay? And they have a very feminized digit ratio. And, well, I've already spoken about the work of Zeng and Cohen on animal models, such as mice. You can look at amniocentesis data, but it's difficult to work with amniocentesis, and usually the samples are taken in the 2nd trimester, so it's a not very reliable way of looking at things. And there is this way, which is very promising. You can look at maternal serum assays for testosterone and estrogen when they're carrying a fetus that's towards the end of the 1st trimester. You don't have to go into and draw amniotic fluid. You can actually look at hormonal levels, either in the urine from the mother or directly from the blood. And that's a very promising way into this problem of trying to directly prove that digit ratio is a measure of prenatal testosterone, prenatal estrogen. Okay, so there are 1 or 2 studies going on already on that, and hopefully we'll be getting results fairly soon on that. So we've got 3 studies, 2 in humans and 1 in a New World primate on that. Okay, so that's a kind of an introduction. What I want to do now is kind of trot through this sex difference, trot through this ethnic difference, and end up with the national differences. Differences in average digit ratio between the UK and the US and Greece and Germany and France and Poland, and see what the some of the implications of those differences in digit ratio are. Here's a sample from the UK looking at sex difference. Here along the x-axis we have age of the children. Okay, these are individuals from 2 years to 25 years, and this is looking at their right digit ratio. Obviously you can measure digit ratio on the right hand or the left hand. The right hand is probably the best one because it seems to be more sensitive to these prenatal sex hormones than the left. Okay, so most of the significant relationships and the significant results we find with right hand digit ratio. So if you're going to try to predict the outcome of a sumo wrestling bout, for example, measure the right hand of both of the wrestlers rather than the left hand. So on the y-axis we've got right digit ratio, and down here they are very androgenized, very testosteronized, and up here they are very estrogenized. And this regression line is the average per year, average digit ratio per year in this sample of 800 males and females. And there's the female line, which is 1, and there's the male line, which is 0.98. Okay, and they're flat. They individuals over a period of 23 years. I just didn't know the time, but this is a cross-sectional study. But basically, I think this is the situation that if you have a digit ratio here, you also have it here and here and here, and as you go through your puberty, it's still there and there and there and there and there. So it's stuck in your fingers, you've got it, and that's it. You can measure directly on the fingers for digit ratio. You can measure x-rays. You can do it very exactly, but you can do it in a rather sloppy way as well and ask your subjects to measure their own digit ratios. So we did that in an online study using the British Broadcasting Company as a means of getting the study online and to as many people as possible. And so we ended up with 117,502 males and 100,144 females, all of whom measured their own digit ratio. There's the mean for the males, 0.984. There's the mean for the females, 0.998. And that is for the right hand. The left hand is rather similar, and that's a significant sex difference. Well, it would be with those kind of numbers. If you look at the standard deviation of those means, that's very high. So if I'd measured those individuals myself, if that was possible, that standard deviation would be half that. Okay, so that's an indication that the measurements are sloppy, but at the center of those measurements is some truth. Okay. Also in these data is this little variable. Okay, right minus left, and in other words, one is looking at the difference in your digit ratio in your right hand compared to your left hand. And that has got some information in it as well, because if you've got a masculinized digit ratio in your right hand and a feminized digit ratio in your left hand, which is fairly common, then that's another indication that you've had high testosterone before birth. So the really, really good athletes tend to have a masculinized digit ratio in their right hand and a rather feminized digit ratio on the left hand. Okay, so there is a sex difference, but is there a sex difference? One of the problems with working with ratios is this problem of allometry, okay? So there is a possibility, because men have longer fingers than women, because they grow taller on average than women, that as their fingers grow, the sex difference arises simply because their ring finger grows a little bit faster than their index finger. So what we end up with is a population of fairly long-fingered individuals, most of which are males, and they've got the sex difference in the relative lengths of these two fingers simply because they've grown a little bit more than females. So that's an objection. Is there really a sex difference? Well, well, I think the answer to that is yes, there is really a sex difference. If you look at what happens when people grow in terms of the lengths of their fingers, here we've got age along here, and this is the length of their 4D, right? Their fourth digit. And the squares, the red squares are females, and the circles are males. And you can see that, on average, male and female fingers are more or less the same length until you get to the age of 12 or 13. And in fact, if you take 4D of males and subtract 4D of females, and if they were equal, that would be 0, so there'd be a line there. Then for children between the age of 2 and 12, actually females have got longer fingers than males, slightly longer fingers than males. But the sex difference is still there. At age 2, here we have digit ratio, and it's kind of bouncing around as you go from 2 to 18. And the difference between males and females, the male digit ratio minus female digit ratio, just bounces around as well. It doesn't really change. All of these differences, except these two, show that males have lower digit ratio than females. But here is the difference in finger length between males and females. Females have got slightly longer digit length until the sexes get to the age of 12, and then wow, males get very much longer fingers. But this does not affect the digit ratio. So the digit ratio is fixed. It's not dependent on digit length. It's not dependent on a statistical anomaly in the allometry of finger growth. You're stuck with it. If you want to look at this issue of allometry, you can look at Klinefelter syndrome. If you remember, I mentioned Klinefelter syndrome earlier. This is a syndrome of the sex chromosomes, and these are males, phenotypically males. They look like males, but instead of having a karyotype sex chromosome of XY, they have XXY. Some of them have XXXY, and some even have XXXXY. Okay. So most have three sex chromosomes, XXY. The birth rate is about 1 in 500 or 1 in 1,000, but there are probably many more Klinefelter's men around because the phenotype is quite variable, and it is quite difficult to detect. One of the constant factors of this is Infertility. Klinefelter's men are very much in general infertile. They don't produce any sperm. They have low testosterone in the fetus, in the newborns, and in adults. And once they are diagnosed, quite a lot of them, but not all of them by any means, take testosterone. And they are tall in general, they're very tall. So if you go to a Klinefelter's gathering, which I've been to Klinefelter's gatherings, I'm the shortest chap in the room. They're all about 6'4", 6'5". Well, not all, but most of them are. So, in general, they don't go bald. They don't have much in the way of beard growth. They don't have much in the way of chest hairs. They've got narrow shoulders. They tend to grow breasts. They've got quite wide hips. The testes are quite small, and they've got long arms. And it says they've got they've got long legs. Long legs, not long arms. And it says that they've got long arms, but they haven't. Okay, they've got long legs, and relative to their legs, they've got short arms. So we looked at Klinefelter's men. There are in England there's a Klinefelter's association, and I go along to their meetings quite regularly. And they're really nice people, very easy to work with, and very interested in the work. So this particular study, we had Klinefelter's individuals, KS individuals, plus their fathers, their mothers, their sibs, and controls selected from the general population. We asked them to take photocopies of their hands because they were scattered all over the country, and I couldn't get around to measuring them all. So we ended up with 51 of these Klinefelter's men, 16 fathers, 15 mothers, 153 male controls, and 153 female controls. There we have the height, the average height of these samples, and here we have the Klinefelter's men. Here we have controls of X and Y, and there we have the females. So they're pretty tall, these subjects. If you look at the average finger length, of Klinefelter's men is about the same. These are standard error bars. Is about the same as the average finger length of an XY male, and both these groups have longer fingers in adults than females. Now, if allometry is important, one would expect that these individuals would have a masculinized digit ratio, because allometry is dependent on the length of your fingers, and they'd have masculinized finger ratios as these individuals have. That's their finger length relative to their height, and these are the means for the digit ratios for these individuals. Here's the Klinefelter's men for right-hand digit ratio, 0.979, which is more feminized than their fathers, who are quite masculinized. Okay, they've got low ratios. Male controls 0.956, so Klinefelter's are more feminized than male controls. 0.969. That's their mothers, and they're actually more feminized than their mothers. And there's the female controls, which are almost the same as the Klinefelter's individuals. And those effects in the right hand are more or less the same as the effects in the left And there's an illustration of the means. Here we have the means for the right hand and the left hand for KS males, Klinefelter's males, and they're very feminized right at the top of this ratio. Here are their fathers right down the bottom, very masculinized. There's the average in the population. And there are the averages for the females, the controls, the mothers, and the general population controls. So these individuals, they've got an extra X chromosome, they've got very feminized ratios, they've had a lot of prenatal estrogen and very little prenatal testosterone. So the effects of allometry are just not there in that. There's the hands of a typical Klinefelter's man. And there's a masculinized XY male. If you look at the differences there. Okay. Stop looking at your fingers. Right, so I've more or less gone over those conclusions for that. Right, we're still on sex, and a few comments about sperm production, because in the 1998 paper, we were working in an infertility clinic in Liverpool University, and we saw some interesting effects. So in a sample of men attending this infertility clinic, we found that when a couple comes into an infertility clinic and they've been trying to have a baby, about half the couple, the problem is with the potential father, and about half of it is with the potential mother. Okay? So the problem is trying to identify which of the two has the infertility problem. We found amongst these patients that male patients who had high 2D40, feminized digit ratios, tended to produce no sperm at all, or had very few sperm. While the low 2D40 males with masculinized digit ratio had normal high sperm counts. So the digit ratio divided these men attending the clinic into two very obvious distinct groups. And then we had people trying to replicate that by, instead of looking at samples from an infertility clinic, they looked in the general population. And Furman et al. Couldn't replicate that result, and Bang et al. Also couldn't replicate that result. However, there was a study in France that looked amongst fertile men in the general population and found that masculinized digit ratio was related to large testes, higher sperm quality, sperm swam in straight lines instead of all over the place, and they had fewer obvious abnormalities. And in this sample, it was of couples who were trying to achieve a pregnancy, and the men who had masculinized digit ratio amongst these couples, they had a shorter time to pregnancy. There is also associated with the trait with feminized digit ratio in apparently normal men. There are problems with the development of the reproductive system, with the formation of epididymal cysts and so on, and some abnormalities of the prostate gland. Right, okay. I'm going to flip over that one. Right, so I hope I've more or less established that there are sex differences in digit ratio, and these sex differences relate to quite fundamental aspects of reproduction. they're real sex differences. They're not influenced, in my opinion, by allometry. And they are sex differences which are established very early and don't change with puberty. Okay, so is that where it stops? Well, it's controversial enough to find a trait that's got sex differences and which go way back into prenatal points of development. It is controversial enough because one can look then at this trait in relationship to a whole host of different things, which can cause some problems associated with the interpretation of human behavior. Is it influenced by genes? Is it influenced by hormones? Is it influenced by socialization and so on? That's a whole range of very controversial stuff. But let's now get out of that controversy and jump into another one and look at ethnicity. I hope there's an exit here when I get out before before you realise I've finished. Right, so, oops, what have I done? Okay, if you look across ethnicities, instead of looking at just males and females, if you look across ethnicities, is there any difference in average digit ratios? Well, the answer is yes. There are substantial differences across large ethnic groups such as Caucasians, East Asians and blacks. Okay? And they are of such magnitude that they're almost as great as the sex differences. Again, let us, in trying to illustrate this, let's have a look at this internet study again. So we've got lots of individuals that we've measured, or they've measured themselves, and we've ended up with, excuse me, 255,116 participants, more or less equal numbers of males. There's the mean age. We've got 6 ethnic groups. These are the groups that the BBC decided they were going to divide the study into. So most of, we've got, the largest group is 214,000 whites, 16,000 Asians. These are individuals from the Indian subcontinent. About 4,000 black individuals, nearly 6,000 East Asians, and mainly Chinese and Japanese, nearly 3,000 individuals from the Middle East, and then you have about 10,000 of mixed ethnicity. These individuals are from 187 countries, but the largest group of individuals are from the UK and the USA. And here are the average digit ratios. So white male, white female, there's the difference, the sex difference. Next group coming down, getting more masculinized, Asian male, Asian female, Middle East male, Middle East female, Chinese male, Chinese female, black male, black female. So we've got male, female, male, female, male, female, male, female, male, female. So females are more feminized in their digit ratio, higher digit ratio than males in all of these major ethnic groups. And we've got this difference, and these two ethnicities, black individuals and East Asian individuals, have got the lowest, most masculinized digit ratios of all, and the highest, most feminized digit ratios are amongst the Caucasians, or amongst the white participants. So from that we can jump into the national differences. Now, obviously we had different numbers of participants per nation. Okay? The 5 largest samples were from the UK, from the USA, from Canada, Australia, and the Republic of Ireland. In order to take out the effect of large ethnic differences, we looked simply at whites because they were the most numerous in the study. So, we needed a certain cutoff point for sample numbers. Once we'd taken that, we had 29 countries which were predominantly white, and for which we could get a mean digit ratio for males across right and left hand, a mean digit ratio for females. We added those two means together and got the overall mean of the nation's digit ratio. Bear in mind that the numbers vary across the nation, so there's some imprecision on these data. And I've ordered these 29 nations from most feminized, if you like, the highest digit ratio of both males and females, coming down and down and down and down to the most masculinized. So up here is Bulgaria and Turkey and Hungary and Greece, and down here is New Zealand and Iceland and Portugal and Australia. Yeah, just let you contemplate that. Okay, now we could probably, what we've done is we've looked at these average digit ratios in relationship to what the gross national product of these nations are, what their cigarette consumption is, what their alcohol consumption is, what their frequency of breast cancer and prostate cancer and cancer of the kidneys and melanoma and a whole range of different things. A lot of these diseases, their frequency, their etiology, are related to these average digit ratios across nations. But I'm not going to look at that and depress you about that. I'm going to look at something else. What I'm most interested in today is not so much that Bulgaria has got the highest digit ratio of the lot, and New Zealand has got the lowest, the most masculinized digit ratio of the lot. What I'm interested in is the difference, the sex difference in these nations. So their average digit ratio, that goes from feminized down to masculinized, has not really got a strong relationship between the sex difference in these nations. What is the sex difference in the UK between males and females? What is the sex difference in the USA between males and females? What's the sex difference between males and females in Bulgaria and the sex difference between males and females in New Zealand? If you look at that, you'll see that across these nations, there are some nations where males and females are quite different in their digit ratio, and there are some nations where they're almost together. There is a bit of a sex difference, but it may not even be significant statistically. That's another way of looking at average digit ratios. Right, so I want to look at differences in sex, sex differences in average digit ratio. And I could look at a whole range of different things in relationship to that. But I want to look at, because I've been controversial throughout the talk, I've talked about sex differences and I've talked about ethnic differences. I'm going to be even more controversial, and I'm going to talk about gender inequality. Right? Sorry. gender inequality varies across nations. How do we define inequality? Where such inequality is defined as the disproportionate representation of one sex over the other in desirable social and economic roles. All right? So that's how I'm going to define it. You might disagree, but let's go with that definition. So that in Sweden, 45% of all parliamentarians are women. In the United Kingdom, it's about 22%. In Poland, it's about 22%. In Romania, it's 10%. Okay? So why is there a difference in parliamentary representation amongst women across these nations, these 29 nations? Well, it might be the result of a whole range of different things. For example, it might be the result of economic prosperity, where the more prosperous nations, for one reason or another, have more women in their parliamentary representation. But it might be partly the result of a biological variable. Okay? Consider a biological variable, the relative degree in which offspring in these nations are exposed in utero, when they're a fetus, to testosterone. And the degree of uterine exposure to testosterone we're going to measure by the second to fourth digit ratio, or 2D40. Males are exposed to more testosterone in utero than females. However, the sex difference varies across nations. And I'm going to look at this difference in the sex difference in digit ratio across these nations, and I'm going to look to see if it relates to gender inequality in parliamentary representation and in female representation in the labour force. What's the proportion of women in the labour force? Okay. Now, in order to do this, I need a simple measure of the sex difference in digit ratio. And the way to do that, I mean, I could just simply do males minus females, or females minus males. But one way of doing it is to regress female digit ratio per nation on the y-axis onto male digit ratio per nation on the x-axis, and run a regression line through that relationship. There is a relationship, so that as male digit ratio becomes more feminized, so does female digit ratio, and there's the regression line. But that regression line is an average. Okay? Above that regression line, that positive area, there is these nations have less female testosterone in utero than the nations below that regression line. So below the regression line, where we have in negative territory, females have more testosterone. Above that regression line, females have less testosterone. And if you calculate that difference in respect to that regression line, you have a variable called the residual. Right? So we've got residuals for these 29 nations. Some of these residuals are positive, and these are nations where females have had lower testosterone, and some of these residuals are negative. These are nations where females have had more. And there's some of the relationships. So, where the residuals are positive, less female testosterone than expected. And here we have, and in amongst these nations, above this line, we expect high gender inequality. The differences, the sex differences in digit ratio are high. Okay? And you expect high gender inequality in Turkey, Croatia, Poland, Czechoslovakia, Hungary. Where the residuals are negative, you expect low gender inequality in Denmark, Iceland, Argentina, Portugal, France, etc. Now, you can plot that out in a more precise way and look at percentage of female parliamentarians per nation. And here we have our negative residuals, where these are nations where the digit ratio of females is very similar to the digit ratio of males. There's a sex difference, but it's pretty weak. And in this part of the regression diagram are the Scandinavian countries. Okay? In the Scandinavian countries, like Norway and Sweden and Iceland and Denmark, they have high female parliamentary representation. And the males and females have got very similar digit ratios. Down here, we have countries such as Bulgaria and Greece, where males and females have got quite substantial sex differences. Okay? To put it another way, if having a lot of testosterone prenatally makes you assertive, okay? I'm not saying aggressive, but I'm saying assertive, then increased assertiveness in females such that it equals assertiveness in males results in high percentages of female parliamentary representation. If low testosterone in females results in less assertiveness, the overall result of that is lower female representation in the parliament of these nations. What about proportion of females in the workforce? We get the same basic result. So in countries where there are a lot of female parliamentarians, there is a high percentage of female workforce representation, and the sex difference in digit ratio is the same. So in countries where there are a lot of women in the workforce, the sex difference in digit ratio between men and women is low. In countries where there are hardly any women, or very much reduced proportion of women in the workforce, the sex difference in digit ratio is high. Now, okay, there might be other factors here. For example, national prosperity, and there is a relationship between female workforce representation and gross national income per capita. So we need to portion that out. And if we look, for example, here at, what is this? Number of percentage of seats in Parliament, there's the effect of digit ratio, there's the effect of gross national product, and there's the relationship with numbers of seats in Parliament, and there's the, let me see, did this not work? Oh, there's the p-value, and it remains significant. There is still a significant effect of gross national performance. If you partial out gross national performance for percentage of women in the labour force, again, you get this significant effect on digit ratio. And basically that says what I've just said. In countries where there are a lot of female parliamentarians, the sex difference in digit ratio is quite small between males and females. In nations where the sex difference is quite large, they have fewer female parliamentarians and they have fewer numbers of women in the workforce. And I don't know whether I've got time to. What time did I start?
I don't think so.
Have I got a minute to talk to this slide?
Sure.
Sure? Oh, okay. This chap's in charge, so the reason I put this slide up is that obviously there are lots and lots of different variables one could look at in terms of digit ratio. And when the whole thing started in 1998, and my group published this paper, there had hardly been a digit ratio paper for 10 years. I think there was one or two, maybe. Since that 1998 paper, there's been 873. And they're across a whole range of different stuff. Some of it totally nonsensical, to be honest. But what biologists tend to do is that then wait until there is maybe 10 studies on a trait, maybe 15 or so, and then they do a meta-analysis. I won't say what I think of meta-analyses because I might use rude words, but there is some merit in meta-analyses. So there's been a whole bunch of meta-analyses on digit ratio studies. Side differences. Sex differences greater in the right hand in digit ratio than compared to the left hand. And that's a real difference. There's a lot of studies on that. Sport, low masculinized digit ratio is related to high performance in many sports. And that's a very substantial effect. So that's real. Autism, masculinized digit ratio is found in children with autism and in children with hyperactivity. That's a real effect. Alcohol consumption, low digit ratio, masculinized digit ratio is associated with alcohol consumption. It's associated with alcohol addiction as well. Video game addiction, low digit ratio, masculinized digit ratio is related to this terrible problem of video game addiction, which has arisen over a relatively short period of time. Sexual orientation, well, masculinized digit ratio is found in lesbians, okay, compared to straight women. Well, maybe. And there's no difference in homosexual men. Well, maybe, don't know. So that's kind of, but some people believe that that's true. Aggression. Low digit ratio is associated with violent aggression, physical aggression. It's not related to verbal aggression, okay? And there's a lot of argument about that. Some of it is politically inspired, I think. But I'm biased. The structure of the androgen receptor gene. Well, I'll skip over that. That's highly controversial. Visuospatial judgment. There are sex differences in visuospatial judgment. However, maybe digit ratio doesn't tell us very much about that. Okay? Masculinity and femininity. Well, how controversial can you get? How do you define masculinity? What are the characteristics of masculinity? What's the characteristics of femininity? We're still arguing about that. Does digit ratio relate to these characteristics? Adult levels of testosterone and estrogen, they are not predicted by digit ratio. If you take your testosterone level now, you look at your digit ratio, there will be no relationship, okay? It's the prenatal levels which are important and which digit ratio picks up on. This living fossil in your fingers which tells you what has happened to you towards the end of the first trimester of your development. Okay? Thank you very much for listening.